Chapter 8 covers reactions of alkenes. There are a lot of reactions covered in this chapter. And the best way to remember is to make a table, like a summary for the chapter, summary of reactions for the chapter. And if you search online, you could get like a summary sheet. It's okay. Your book has a summary sheet that it covers all the reactions of alkene, like addition reactions of alkenes, and is going to, make it easier. Just make sure that you memorize the reagent, because you have different reactions. You want to make sure you know the reactant, reagent, and then product. Reagents are, or you get like multiple reagents for the same type of reactions with like a specific, either if you're getting like a specific product based on addition, if it's going to be Markovnikov addition or anti-Markovnikov addition. So for a specific condition, you have to remember the specific condition. Which one are you going to use? Okay. It gets a little bit more in detailed. Like if you are like a good cook, you probably use different type of meat for like beef stew compared to the steak compared to, so you have to look for the type of the, like it's not just the red meat. You have to pick the right part of the meat for what you are going to make. So it's a little bit more detailed. Alkene, they are more reactive than alkane. We did talk about it briefly in chapter 7, because alkene, they contain carbon-carbon double bond. Out of a carbon-carbon double bond, for these two bonds, that we have one pi bond and one sigma bond. Sigma bond, it's
Professor?
like yes.
Okay, sorry. I'm sorry. I know you asked if we had questions, but I just thought of this one because I thought of the OR assignment. So I'm a little confused as to what the deficiency in hydrogen is. I was trying to work on the chapter 7 OR, and I'm a little confused on.
Okay, good questions. It's actually in time for this for alkene. I can explain under this chapter, but you see that if you have two carbon, and you have 6 hydrogen, that is a 2n plus 2 for general formula of alkane. You see, you have for every carbon you have 3 hydrogen. For every carbon you have 4 bonds. The number of hydrogen comes like secondary. It's not that important, but number of bonds for carbon is very important. So this is the case that you had a saturated hydrocarbon C2H6. Now, if you have a molecule of a C2H4, okay, you draw your carbon. There should be a carbon-carbon bond, definitely. And then you distribute the hydrogens. To be fair, you have 4 hydrogens. You are going to give 1 hydrogen to 2 hydrogen to carbon on the right side and 2 hydrogen on carbon on the left side, and you don't have any more hydrogen. Now, you have this structure here, but is this structure stable? Yes or no?
No, because it's not fulfilling the octet.
It's not stable because carbon must have 4 bonds, right? Carbon must have 4 bonds and is not filling the octet. 4 bonds meaning 8 electron or octet rule. Now it's not stable. So how this, if you were drawing the Lewis structure, you were going to share like electrons in order to make a double bond. So if I had enough hydrogen, I didn't have to make double bond, right? If I had enough hydrogen, I didn't have to make the second bond, the double bond. Because in the structure that I have on the left side, since I have 6 hydrogen, there is no double bond here. The structure on the right side, I only have 4 hydrogens. And since I have 4 hydrogens, then that means this molecule is hydrogen deficient. So you could feel that hydrogen deficiency here. Right? How many hydrogen is missing?
2.
This is 2 hydrogen is missing. And every 2 hydrogen that is missing, you get like 1 pi bond. When we talked about the alkene structure of the alkene in chapter 7, we said alkene has carbon-carbon double bond. That means any alkene, if it is monosaturated, unsaturated, or it has like only 2 hydrogen missing, is going to have 1 carbon-carbon double bond, at least in the molecule. So it's hydrogen deficient. Now, if you had a C3H6, what is the hydrogen deficiency? How many hydrogen is missing? C3H6, how many hydrogens are missing? What should be your reference? What should you compare to?
The original.
Original, which is C3H8, right?
Yes. So then you're missing 2.
2n plus 2. So if you have 3 carbon, you must have 8 hydrogen to be to have no deficiency, hydrogen deficiency. And that comes from this general formula, beginning of chapter 7 we covered.
So you're missing 2 hydrogens in that case,
So
right?
we are missing, in this case, we are missing 2 hydrogen. So it's 2 hydrogen missing. And if you're missing 2 hydrogen, that gives like 1 pi bond. Now, if you have a new compound, the purple color, C3H4, how many hydrogen is missing?
4.
4 hydrogen is missing. And what is the reference? The reference is the CnH2n plus 2. The reference is for every 3 carbon, you need 8 hydrogen to have no hydrogen deficiency. And since you needed 8 hydrogen, but you only have 4 hydrogen, the difference of 8 minus 4 equals 4 hydrogen is missing. If 4 hydrogen is missing, that is equivalent to 2 like pi bond. So you could have like 2 double bond or 1 triple bond. So that's the hydrogen deficiency is going to be 4 in this case. Okay.
You always want to remember the formula for you to be able to go backwards and.
Yes, the reference. The reference is like if it's fully saturated. If it's fully saturated, that means the formula of CnH2n plus 2 applies. And you're comparing the given molecule, given structure to the expected. Like in theory, in order to have no hydrogen deficiency, how many hydrogen it should have had. Okay, did they answer your question?
I have a question regarding that assignment because I'm trying to figure out for one of them, and it has like oxygen, nitrogen, and hydrogen. How do we figure out when it's that many different elements in there?
Okay, is this a co-op assignment or OR assignment?
It's that assignment that you posted on chapter 7. I'm just trying to like see how to figure it out. You give an example similar to it. So
sure. What's the formula?
it's aspartame. That's what it's called.
Okay, what's the formula? The molecular formula?
Give me a second.
How many carbon, how many hydrogen, and how many oxygen, how many nitrogen?
So there is 14 carbons, 5 oxygens, 2 nitrogens, and 18
Is
hydrogens.
the C14H what?
There is 18 hydrogens.
18. And oxygen is
There's 5 of them.
5 oxygen. And how many nitrogen?
There's 2.
2 nitrogen and what? Any halogens?
No.
No. Okay. So what do you count the nitrogen for? Nitrogen equals to how many carbon?
It's a half, right?
Half
0.5,
carbon.
yeah.
0.5 carbon. Okay. Since you have 2 of them, it's going to be 1 carbon. And what about the oxygen?
Wasn't it 2?
No, oxygen we don't count.
It doesn't count as anything, yeah.
Doesn't count at all. Yeah, we don't count the oxygen.
Even when it's an alcohol, like when it's an OH?
Yes, we don't count the oxygen. We count the hydrogens, but we don't count the oxygen. From the OH, we count the hydrogen, but we don't count the oxygen. Okay, if you had 14 carbon, how many hydrogen should have been there? I'm sorry, you don't have 14, now you have 15, right? You have 15 because it's the 2 times 0.5 to 2 nitrogen, 0.5 times 2 is going to be 1 carbon and 14 carbon, so we have 15 carbon. So we have 15 carbon, what should be number of hydrogens?
So wouldn't it be 32?
Yes, 32. We need 32. How many hydrogen do we have is 18. So 32 minus 18 is going to be 14. Right?
So it'll be about 7 then?
14 missing hydrogen.
7
Well,
pi
4 to
bond.
7. Yeah.
Yeah, 14 missing hydrogen, and that counts as, if you divide it by 2, you divide this by 2, it gives you 7 element of unsaturation. 7 element of unsaturation.
What were the elements that counted as a hydrogen? Halides?
Halogens.
Halogen?
Chlorine, bromine, iodine would count as hydrogen.
Isn't there a third one? I know it was oxygen, nitrogen. There was one more, wasn't there? Or
It's
was it just
possible.
Okay.
So how come we don't count oxygen? What's the reason behind that?
This is convention. Someone came up with the rule, the same way that by convention or by the rules we are dealing with the octet or dealing with the IUPAC rules is by convention. So we're just following the procedure. Like did you count oxidation number for oxygen to be 0 as a O2 and a -2 in oxide and -1 in peroxide? Those are the, kind of is a procedure already, is established procedure.
So for the questions like this, do we answer strictly by, or like what the answer would be, like we would be missing the exact number of hydrogens, that's it? Just the exact number of hydrogens that are missing?
Depends
There's
on
no
what the question is asking. Is the question asking how many elements of unsaturation you have, or what is the possible structure? So it depends on the structure, what the question is asking. But
because it doesn't mention unsaturation, like at least the questions that I've seen, they don't mention unsaturation, just hydrogen deficiency.
Okay, hydrogen deficiency is going to be 14. Hydrogen deficiency.
Are those synonymous?
Then that is like if it's translated to number of pi bonds, it's going to be like 7, or cyclic system. We had that. I know that we had 2 examples based on that in chapter 7. Cyclic system counts as 1 element of unsaturation, and then the pi bond counts, or hydrogen deficiency for every 2 hydrogen missing is 1 bond or 1 pi bond.
What if you have a different element? Like, let's say instead of having oxygen, you have like chlorine, then how would you figure out the deficiency for hydrogen?
I think that was a question that someone asked earlier. I think it was Joseph who asked, or someone asked. We had that beginning of chapter 7. Chlorine replaces hydrogen. So if you have 1 chlorine and 13 hydrogen, that counts like 14 hydrogens.
Yeah, that's the third one I was asking about.
Yes.
There was one of them that counted as 1 oxygen, so it must have been
Yes.
chlorine.
Yeah, all the halogens do.
Halogens count as hydrogen. So if you have, for example, if you have a C3H7 and then Cl, hydrogen deficiency for this one is going to be 0, because for 3 carbon, you have basically 7 hydrogen and one halogen that counts as 8. So halogen counts as hydrogen.
If you had a cyclohexane with a double bond, that would be 2 elements of unsaturation, right?
Exactly.
Okay.
It's a cyclic system and a double bond. Yes. Okay. So what do we know about the double bond? So far, a double bond is pi bond and a sigma bond. Pi bond is a weak bond, so you can basically break it much easier than a sigma bond. And if you can break it easily for hemolytic or heterolytic cleavage, as I said in the previous chapter, this is like a hemolytic, like a heterolytic in this case, a cleavage. That means the pair of electrons went to this electrophile, the other carbon takes the positive charge. So when electrophile comes in, doesn't bring any electron and wants to form bond with one of these two alcohol. I'm sorry, one of these two carbons. So in order to form bond, you need electrons. So pi bond is 2 electrons, sigma bond is 2 electrons. So in order for this electrophile to form bond with the carbon, is going to consume or use the pair of electrons from the pi bond, the sigma bond still stays intact. What happens to carbon on the left side? What happens to this carbon? How many electrons does the carbon on the left side has now? Compare the two structure. Comparing structure 1 or A and B. Carbon on the left side, how many electron carbon on the left side has in this structure? A. In the structure A. Count it quickly, please. That's simple.
How many electrons?
Yes.
It has 8.
8 electrons. How many electrons for this carbon we have in structure B?
8.
8.
Also 8 electrons. And what happens to the carbon on the right side? In structure A, you have 8 electrons, right?
Yeah.
The shared electron counts twice. It counts toward both of the nucleuses. And what happens in structure B? What happens to this carbon? Has basically lost the pi bond to the carbon on the left and has only 6 electrons. Only. If it has 6 electrons, it's going to gain the positive charge. So from now on, anytime you see a electrophile coming and forming bond with the one of the two carbons of carbon-carbon double bond, the other carbon would take the plus charge. So one carbon takes the electrophile, the other carbon takes the plus charge. Please keep that in mind. And if you didn't get this explanation here, watch the video one more time because it's very simple. Because it requires, electrophile requires electrons to form bond with one of these carbon, is removing electron from the pi bond. So it doesn't affect the overall charge or number of electron for the carbon that is taking the electrophile because it still has the 8 electron, but the other carbon is going to be electron deficient and is gaining plus charge. Now, on the next step, if you bring a nucleophile that has a negative charge, positive charge, they're going to cancel. This negative charge is coming because it's assigned here because your nucleophile has pair of unshared electron. So when nucleophile wants to form bond with the carbocation, is bringing this pair of electron to the center and is sharing the pair of electron between the carbon and the nucleophile. And if you have a negative charge, positive charge is going to cancel. Let's say if you brought here, instead of this nucleophile, if you brought H2O, H2O has pair of unshared electrons, but it doesn't have negative charge. It's not like hydroxide with a negative charge. If you bring this, the pair of electron can be shared, but the positive charge is not going to be canceled. So you just have to make sure that to understand when electrophile comes in, because it's bringing the plus charge, it's going to bring in and make the product positively charged, overall positive charge. And when the nucleophile comes in, the nucleophile is going to cancel this positive charge. You do need something to cancel this positive charge, because if you bring a neutral nucleophile, the positive charge will not be cancel. Just keep that in mind and you will see the examples that I'm talking about.
So basically one's gonna lose and one's gonna gain.
When it's plus minus, there is
Yeah.
going to, plus and minus is going to cancel the charges, yes. The one with the minus charge is going to bring a pair of electrons because the one with the plus charge brings no electrons. And they would share now is going to be, the charge would be canceled.
So if it was just water and not a nucleophile, that would just be saturation, right?
In terms of the hydration, you mean? No, you are going to still bring H2O is going to attack, and we will see one of the mechanisms that H2O is going to form bond with carbocation, but then you have to remove the H plus because the plus charge cannot stay there. If the plus charge stays there, it's going to be is going to make the molecule charged molecule, and charged molecule is not product, is intermediate. Until you remove the plus charge somehow, you're not going to have a product because it's still intermediate. That's the difference between intermediate and a product. Your product is going to be neutral. Okay, this table has a summary of the whole chapter 8, but you need to learn about the difference between let me see if you have the, no, you don't have the different method of hydration. So it's not the whole chapter. Most of the chapter is covered here. Different type of addition reactions that we see for alkene. So starting with the alkene, you start with the alkene and you're making alkene go through addition reaction. One thing you want to remember by heart is going to help you a lot. When you add water, the reaction is called hydration. Add H2O, the reaction is called hydration. What is happening in hydration, you're adding H plus, and you're adding OH minus. So you're not adding 2 hydrogen to one carbon and then oxygen to the other carbon. In hydration, you're adding H to one carbon and OH to the other carbon. Since you're adding OH to the other carbon, your product is going to be alcohol. So when you say hydration, and earlier someone mentioned this as a saturation, like being saturated, like gaining water, you have to be a little bit more specific in this reaction, because when you say hydration is gaining water, it's not absorbing water that it can lose, it becomes part of the molecule. So it's known as the hydration. Hydrogenation. So what does hydrogenation, if hydration means adding water, what does hydrogenation means?
Adding 2 hydrogens.
Adding hydrogens. Okay, hydrogenation meaning adding hydrogens. So because you have the pi bond, you break the pi bond, and you make 2 sigma bonds. In all these reactions, you see that you break the pi bond and you make 2 sigma bonds. So you have the 1 hydrogen added to each carbon. So what does halogenation means?
Should be like 2
Adding
atoms of
halide.
halogens. Yeah.
You're adding halogens, and you're adding 1 halogen to each carbon. So you have hydration, you have halogenation. And if you combine these two, halohydrane, what does it mean? Halohydrane. That means halogenation and hydration together. So you're adding a halogen and you're adding a hydroxide. So it kind of, if you look at the meaning of these words, is going to help you to remember more. So addition of HX, like if you're adding HCl or HBr, okay, or if you're adding HI, H will add to 1 carbon and X would add to another carbon. So this is like more simple. Hydroxylation, that means you're adding hydroxy group. So you add 1 hydroxy to each carbon. You're breaking a pi bond again, you're making 2 sigma bond with OH group. Oxidative cleavage. what does that oxidative cleavage mean? And again, this is just a summary. We are looking at the detailed reactions of all. In oxidative cleavage, what's going to happen, you're going to cleave the double bond. And then it says oxidative, you're adding oxygen to one side and oxygen to the other side, oxygen double bond to each side. That's oxidative cleavage. You cleave the double bond, you add double bond O to either side. Epoxidation, epoxide is the carbon-carbon bond forming a triangle with the oxygen. This part of the molecule is called epoxide. Epoxidation is like inserting oxygen between the two carbon and making this triangle, and that is epoxidation. So this is the summary of the reaction. What you need to know for each of this reaction, what are the reagents used, and beside the reagents that is used, what is the mechanism for the reaction? What will happen first? Okay, first reaction is like addition of HX. So it's the electrophilic addition reaction that you have here. So electrophile comes in. What part of this molecule would act as electrophile? So if you're adding HBr, think this way, you're adding HBr, that basically means that add H plus and you add Br minus. Okay, what happens if you add H plus? Is H plus as electrophile or nucleophile? Is this electrophile or nucleophile?
Electrophile.
Electrophile, very good. Is electrophile? Br minus is going to be nucleophile. Since we know we have electrophile and nucleophile, which one should come in first? Electrophile or nucleophile?
The nucleophile? No.
Okay. Let's say if you were going to bring the nucleophile, and if you look at this area of the alkene, you have 4 electrons shared between 2 carbon. So this area of the molecule is electron rich. Okay? Because it's electron rich, you can force the nucleophile, but is not very excited about, the nucleophile is not that excited because nucleophile has extra electron, and you have CC double bond has already 4 electrons in there, so it's high density of electrons. If you have high density of electrons, a electrophile is going to be more welcome. So it takes less energy for electrophile to come in rather than the nucleophile. So electrophile would come in first. Electrophile that we have here is the H plus. What happens when you get the H plus to one of these 2 carbon? Which carbon would take the H plus in this case?
Second one?
Okay, it shows second one, but is there any difference between the 2? Which one should take based on what is shown on the board? There's no difference, right? In this case, there's no difference. If the second one takes if this one takes the H, the other one would take the plus charge. If this one takes the H, the other carbon would take the plus charge. And since this is symmetrical, is exactly the same, it doesn't matter which one takes the hydrogen.
So what would you do if it wasn't symmetrical?
If it's asymmetrical, then we have to see the other one that is taking the plus charge, which one would be better off to take the plus charge? If it generates like primary carbocation or if it generates secondary carbocation. And that's the major difference between the 2 if it's asymmetrical. Because first electrophile comes in and it forms the carbocation. Now, whichever is the more stable carbocation would be preferred. So in this case, based on the shown structure, it doesn't matter which one takes the H, as long as the first one takes the H, the other one would take the plus charge. Then the nucleophile comes in. Because nucleophile has a negative charge and you have a carbocation, new bond would form, and the net result of this is addition of H and addition of Br, or addition of H and addition of X in general. So in the first step, H plus would come in, and then second step, the Br would come in. So electrophile comes in first, carbocation forms. Next step, nucleophile would come in, and addition would take place. And the nucleophile is going to cancel the charge of the carbocation, and you have the net product of the alkyl halide, because halogen is being added. When hydrogen adds, it doesn't add functional group. But when halogen adds, it adds like a new functional group. So we have the molecule defined or classified as now alkyl halide. Okay, for a symmetrical alkene, it doesn't matter which one takes the chlorine and which one takes the hydrogen. It really doesn't matter. What about this one? Which one would take the hydrogen? Which one would take the bromine?
I mean, are they all the same?
Perfect. They are both the same. So it doesn't matter which one would take the hydrogen and which one would take the Br. Whichever takes the hydrogen, the other one would take the Br. In this case, you also have a symmetrical CC double bond. It is completely symmetrical. The top and the bottom is the same. So as long as one takes the hydrogen, the other one would take the iodine. And then you would have iodocyclohexane, regardless if it's on this carbon or this carbon. You're going to have iodocyclohexane. And because it's symmetrical, it's not going to make a difference of which one would take the H plus. Now, your question, because you asked, what's going to happen if it's asymmetrical? In case that is asymmetrical, the hydrogen is going to add first of all, because we have a carbon-carbon double bond, electrophile would come in first, carbocation forms, and then the nucleophile would come in. Now, which one is going to be major product? Which one is going to form? If hydrogen goes to carbon 1, if hydrogen attacks the carbon 1, if hydrogen comes here, the other carbon will take the plus charge, right? And that gives you a tertiary carbocation. If hydrogen attacks the carbon 2, the other carbon will take the plus charge, and your other carbon is a primary alkyl halide, primary carbocation. So you have a tertiary versus primary. Which one is favored?
Tertiary.
A tertiary. A tertiary carbocation is going to be more stable. And because a tertiary carbocation is more stable, then that would give you the major product. The other product, because it's a primary compared to tertiary, tertiary is a lot more stable than primary. The other one doesn't form. It says not form. And the reason it doesn't form, because the intermediate that forms is going to be very unstable for the primary carbocation. And we are comparing primary with tertiary. Tertiary would take over, the major product, definitely.
So you gotta basically figure out which one will become more stable when it comes to attaching the H to either side.
Yes, because whichever takes the hydrogen, the other one would be the plus charge. So you have to see which plus charge is going to give the plus charge, and which carbon is going to give more stable alkyl carbocation, sorry. So if you have a tertiary carbocation, it's going to be more stable than secondary, more stable than primary, and more stable than methyl carbocation. We already know this from SN1 reactions. So if you have a methyl carbocation, it's going to be the least stable because it doesn't have any other carbon bond, and is not going to get electrons from the other other group. The more alkyl group you have around the carbon that has the plus charge, the more stable that carbocation going to be. And that's what makes the tertiary carbocation more stable than secondary and more stable than primary. Because you have like an empty orbital on the carbocation. Now electrons can go from the groups attached to it. They can overlap, or they can hyperconjugate, and they can support this plus charge for the of the carbocation. If it's a tertiary, you have 3 groups. If you have a secondary, you have 2 groups that they can hyperconjugate with this carbon with the plus charge and give some electron. They're giving some electron. Okay? But you have 3 groups that is giving electrons. So it's going to make the carbocation more stable. Right. Asymmetrical alkene. You're adding HCl. Which one would take the hydrogen? Carbon 1 or carbon 2? And what's the difference? If carbon 1 takes the hydrogen, carbon 2 would be carbocation, which is a secondary. If carbon 2 takes the hydrogen, carbon 1 would take the plus charge, and that is a primary. So you are comparing primary versus secondary intermediate. And primary intermediate is much less stable. And compared to the secondary is going to be the major, the more stable intermediate yields major product. Any questions about?
So it kind of looks like if you make it like a symmetrical figure, it ends up being the correct problem, right? Like the secondary, it looks like it's symmetrical. There's 2 CH3s on both sides.
The more groups, yes, the more groups attached to the carbon with the positive charge, the more support they get, and then more support or hyperconjugation or electron support, then it's going to make the carbocation more stable. Okay, so did you understand this addition of HX? Okay. Addition of the HBr and HCl, we looked at it already. Let's look at a couple more examples. Addition of electrophile and the nucleophile. When you are adding HI to this structure, which one would take the hydrogen and which one would take the iodine? And let's look at why this is we have a minor and a major product. Under what condition you would have a minor and major? You would have minor and major for symmetrical or asymmetrical?
Asymmetrical.
Asymmetrical. So in this case, we are going to have, we do have asymmetrical, right? What makes it asymmetrical? Your carbon on the right side that carries the carbon-carbon double bond is attached to 2 other alkyl group, and the carbon on the left is attached to only 1 alkyl group. So it's asymmetrical. Then you have the hydrogen can attach or can form bond with carbon 2 or carbon 3. If it's a carbon 2, then you would get, if hydrogen attaches to carbon 2, then you would get a secondary carbocation. If this is the case, then you are going to get this product and the secondary carbocation. If hydrogen attaches to carbon number 3, you would get a tertiary carbocation, and then iodine comes in. So the major product, it sounds to be, or looks to be that hydrogen is attached to carbon that has more hydrogen, and iodine or the nucleophile is going to attach to carbon that is more substituted or has least number of hydrogen. And from now on, you are going to, if you look at the alkene first, if it's asymmetrical, then you count the number of hydrogen on the 2 carbon that carry the double bond. How many hydrogen you have on this carbon is going to be 0, right? 0 hydrogen. And on this carbon, you have 1 hydrogen. So 0 hydrogen and 1 hydrogen. Hydrogen is going to be added to the carbon with greater number of hydrogen. And the term is used, rich gets richer. That's the term actually is used in all organic chemistry books. It says the carbon that has more hydrogen will gain the hydrogen. The other carbon gain the nucleophile. That's why the first product here is a major product. Hydrogen is being added to the carbon that has already 1 hydrogen, and iodine is being added to the other carbon. And the other case is your minor product. So what happens in 1-methyl cyclohexene? Which one is going to be major product? So in this case, you also can count the number of hydrogens. How many hydrogens you have on this carbon? And this carbon, can you see this carbon? Can you tell me how many hydrogen you have on that carbon?
One.
One.
One hydrogen. So we have 1 hydrogen here. And how many hydrogens you have on this carbon?
0.
0 hydrogen.
None.
None. Or 0 hydrogen on that carbon. How do you count this 1? Because carbon is tetravalent, it must have 4 bonds. And for the line angle structure, any bond that is not shown, but it needed to be, is going to be hydrogen. So it shows 3 bonds. The one that is missing is hydrogen. For the hydrogen and the tertiary carbon that we have here, there already we have 4 bonds attached to carbons. So there is 0 hydrogen. So carbon that has more hydrogen is going to be carbon to the right side, and that's the one that is going to gain the hydrogen, and that makes this major hydrogen, major product. Carbon with more hydrogen would gain the hydrogen, and carbon with least number of hydrogen would gain the Br. This product, or having this pattern for the product, is known as the Markovnikov product. So the product is the Markovnikov product. So in this case, carbon with greater number of hydrogen is going to gain 1 more hydrogen. So hydrogen is going to go to carbon 1, and the Cl would go to carbon 2 because carbon 2 has 1 hydrogen, carbon 1 has 2 hydrogen. Carbon with more number of hydrogen will gain the hydrogen. And it's known as the Markovnikov rule. For addition of alkene or addition of the HX to alkene, or addition of water to alkene, in addition reaction in general. If you get this as a major product, it's called Markovnikov product.
Professor, I'm sorry to interrupt, but I know the quiz starts in 2 minutes, and on my end, it's still showing that it requires honor lock.
Okay, yeah, you need to refresh your page.
Yeah, I have.
You have refreshed the page. It
Yeah.
doesn't show any honor lock. Did anybody refreshed and didn't see the honor lock?
Yeah, it showed
honor lock for me.
Me too, Professor.
It still shows as honor
Same
lock?
here.
Yes.
Yes.
Oh, okay.
Thought I'd make you aware before people start taking it.
Okay.